Hello, I am Suvendu Nayak from IIT Bombay. The topic of today's presentation is towards rugged silicon carbide technology for electric transportation. This work has been done in supervision of Professor Swaroop Ganguly from IIT Bombay and Professor Anant from Ohio State University. I am presenting this work as IITB OSU Frontier Scholar. The goal of this project is to identify failure mechanisms for silicon carbide power MOSFETs and to develop design approaches to overcome them. In the background, the material properties of silicon carbide itself is far more superior than silicon when it comes to high voltage application. This is demonstrated in the left-hand side figure where the material properties of silicon and silicon carbide is compared. The device made by these semiconductors have wide applicability, essentially in renewable energy sector and EV sector. This has been demonstrated by the market projection of power silicon carbide devices in the figure below. Design innovation for existing problem is the key motivation for this project. This project has been investigated via simulation. The simulation deck is validated by matching the simulation result to the experimental data. This is called calibration. The calibration here is multidimensional, as we have calibrated it against various dependencies. They are temperature, doping, and voltage. So in the first figure, the calibration is done against a simplest device structure, and in the second figure, the calibration is done against the special device structure which is used in high voltage application. This is called DMOSFET structure. We have done design modification to overcome the existing issue. Silicon carbide device being used in high voltage application has to face short circuit conditions. In our houses, we have a fuse to protect us from short circuit condition. But silicon carbide device is not engineered to handle it. So we have modified the design of the silicon carbide DMOSFET to enhance the performance of the device under such conditions. This is shown in figure 3. We have done design innovation to harness the process advances. So recently there has been reported that the silicon carbide and SiO2 can be fabricated with very low interface traps. So we have modified the conventional design structure of a silicon carbide DMOSFET to have the robustness as before, but with low interface traps. So this is shown in figure 4. The simulation result is analyzed and examined with the theoretical knowledge we have on the devices. After all this, we are documenting significant results for the scientific community. In the summary, we have calibrated the mobility models. We have calibrated the silicon carbide DMOSFET. We have modeled the short circuit performance and modified the design to enhance the performance in a short circuit condition. We have modified the design of a conventional DMOSFET to adapt to the low interface defects that are there in the SiC and SiO2 interface. In the next step, we are planning to do device termination analysis. We are planning to measure silicon carbide devices experimentally. Our team consists of Professor Anant from Ohio State University, Professor Swaroop Ganguly from IIT Bombay, and Sujana Hema from OSU, and I am Suvendu Nayak from IIT Bombay. Thank you very much.